Alright, calm. It's AQA A level chemistry topic one pattern, yeah? All of atomic structure, yeah? If you got any questions, anything, yeah, leave it send it to the email and I'll get back to you, yeah? Because honestly, obviously, this is not gonna bang goose or nothing, man. It's just a community thing, you get me, fam. So whatever you want to improve, whatever you want to change in the lesson here, just send it in and I'll pattern it. Alright, calm. John Dalton, yeah. John Dalton was an English school teacher who first wrote that atoms were the basic unit of chemistry, yeah. He thought that atoms were spherical and different spheres constituted different elements, yeah. Dalton thought atoms were the fundamental units of matter and were indivisible, yeah. So he thought that hydrogen and carbon were just different because they're just different, like they're just inherently different, yeah. Essentially. So like carbon would be a sphere, oxygen would be a sphere, iron would be a sphere, and they're all just different spheres, but they're not made of anything. There's nothing deeper than that. Then J.J. Thomson came here, 90 years after Dalton, yeah. J.J. Thomson discovered that atoms were divisible. He discovered the electron. By discovering the electron, he disproved Dalton, yeah, because that proved that therefore the atom is smaller. And you might think like, oh, Dalton is a dumb idea or something, yeah. But obviously, bro, at the time that was fundamental, innit? That was revolutionary, you know what I'm saying? You know what I'm saying? Yeah. And the electron was measured to be several orders of magnitude lighter than the atom, proving that smaller particles than the atom existed. So what happened to J.J. Thomson, yeah, he led to the development of the plum pudding model, yeah. If you man ever as like a youth when you were like four or something, yeah, like you know what I'm saying, if your mum or whatever took you to like some next, you know what I'm saying, and some mall or something, yeah, them like you know them play pit or whatever the fuck, like the ball pit, yeah, with the plastic balls and that. So it's like the plastic ball, yeah, would be that's like the shell of that ball, the plastic part, yeah, would be positive, yeah, and then inside there's just electrons, yeah. So it's just a positive shell with negative electrons inside scattered, yeah. They call it like plum pudding in it, some you know what I'm saying, some English shit, man. But yeah. And the atom is viewed to be largely positive charged square with embedded smaller negatively charged electrons, yeah? Calm. Then Rutherford came here. Rutherford fired alpha particles at a thin film of gold. If the plum pudding model was legit, the particles would have been deflected by the gold, right? Because deeper, if there's electrons inside, it would have deflected the alpha particle. And instead, most particle, not even the electrons, even that the shell would have deflected it, yeah, because the alpha particle has positive protons, yeah, and the shell is positive according to Meyermann's model, yeah. So therefore, the shell would have repelled the alpha particle, yeah. Instead, most particles pass through the film. This led to the nuclear model where the atom was viewed as being mostly empty space with a positive nucleus orbiting electrons, yeah. So because most alpha particles, yeah, just move through the electrons, just cut through the electron, yeah, from not the electron, cut through the atom, yeah. Therefore, it proved that the atom was mainly empty space, yeah. And to understand this, yeah, a teacher once told me in it, take this with a grain of salt in it, because I don't know if that teacher's talking facts or not, yeah. But allegedly, yeah, relatively like the distance from like London to Southampton, yeah. So from Central to Southampton, yeah, that's the same distance between like electron shells, yeah. So imagine between all that area is just empty space. Like one electron will be in Central, one electron will be in Southampton, yeah, and between them is just empty space, fam, yeah, allegedly. Gone. Some alpha particles were deflected, yeah. Reason being is because obviously the nucleus is still positive, yeah. So therefore, when the alpha particle came close to the nucleus, alpha particles also have positive protons, yeah. So they would have deflected, yeah. Some bounce back directly. That's when they directly hit the nucleus. That proves that in the nucleus is a small, dense area, yeah. And sometimes I ask you, yeah, like why gold was used, yeah. So that's because gold is highly malleable, allowing it to be hammered into extreme thin sheets, yeah. 'Cause ideally for this, you want small atoms, yeah. I mean, you want like something that's only atom thick, yeah. Because if you have like bare atoms, yeah, it's gonna interfere with each other with the experiment. So you want like only one or two atoms, like ideally, yeah. And also on top of that, gold is pretty big, so it's easy to measure the effects, yeah, because it's bare neutrons, yeah. Niels Bohr. The nuclear model had a problem though. Classically, an electron should spiral into the nucleus, and the atom should collapse because deep it. If there's what Rutherford is saying is that there's just electrons moving around the protons, yeah. If that was real, yeah, then why wouldn't the electron be attracted into the proton? The proton is positive, so why wouldn't it be attracted into it? Yeah. These are questions that people don't really ask like that. Even in GCSE, you don't really ask that. Like, you see the protons, they're in the nucleus. Why do they just stay there in the nucleus? Why don't they repel? Protons are positive, yeah. Positive and positive, it should repel, yeah. So why doesn't it just repel? So the reason for that one, by the way, you don't need to know about it, but it's something called a strong nuclear force here. And the strong nuclear force here holds together the protons here, so that they don't repel away from each other. And then when they get too close here, it switches. It becomes repulsive, so it repels the protons away from each other a little bit, yeah, so that they don't collide on itself, yeah. So Niels Bohr he solved this problem by developing the first quantum theory of the atom, yeah, which electrons are assigned to a fixed orbit of defined energy, yeah. So he said that electrons worked in energy shells. So this has a particular energy, this has an energy, this has an energy, yeah. In order for it to move down into the nucleus, it would have to lose energy. And for it to go higher up, it would have to gain energy. So it's fixed in those shells. It doesn't just move in and out. Yeah, it requires energy to move them. Yeah. And when electrons move between orbits, yeah, they must emit or absorb electromagnetic radiation of a particular frequency. Essentially, what that means is basically they just have to absorb or emit energy, yeah? Because electromagnetic radiation, it means it's a photon, yeah, light energy, yeah? Or UV or whatever. So yeah, so that's just energy essentially, yeah? So basically, when an electron moves down, energy is emitted, and then when you put energy into something, it moves up, yeah? It's a higher energy level, yeah? So these are particles. This should be easy, man. Proton's got relative charge of +1, relative mass of 1. Neutron and neutral, yeah, has a charge of 0, yeah, and then a mass of 1. And the electron is negligible mass here, 1 over 1840, yeah, and has a -1 charge, yeah. Electron shells and subshells, yeah. So you can think of the atom like a house, yeah, with different floors. Each floor represents an electron shell. The first floor can hold up to 2 electrons, the second shell can hold up to 8 electrons, and then the third shell can hold up to 18 electrons, and so on, yeah. Electrons like to fill up from the lowest energy shell first before moving to the higher ones, yeah. Now, within each shell, there are different rooms called subshells, yeah. These subshells are labeled with letters S, P, D, and F, yeah. Now, this isn't necessarily higher than each other, they're just different rooms within the same floor of the building, yeah. Each subshell can hold a certain amount of electrons. S can hold 2, P can hold 6, D can hold 10, and F can hold 14, yeah? Calm. So it's easy. You got an atom, yeah? You got levels to the atom, yeah? And the higher you go up, the more energy is required. And that's it. And each level has S, P, D, and F. Mass number and isotopes, yeah? So mass number is shown using the symbol A, yeah? And is a sum of protons and neutrons in the atom. That's it. That's all you have to say, yeah? Mass number is proton number plus neutron number. That's it. Atomic number is shown using the symbol Z, yeah? And it's equal to the number of protons in the atom. So the number of protons will be the atomic number, yeah? That's what defines it chemically, yeah? The mean mass of relative atomic mass here. This is a very important. You need to know this like the back of your hand here. This here is like life or death. You get me? Yeah. This is very important. Yeah. So the mean mass of an atom of an element is of an element is defined by the relative atomic mass here is defined by the mean mass of an atom of an element, yeah, divided by 1/12 of the mean mass of a carbon 12 atom, yeah. Now you can change around the definition a little bit. So like the mean mass, you can say average mass, yeah? Or instead of divided by 1/12, you can say on the same scale as 1/12 of the mean mass of a carbon 12 atom, yeah? But it's like driving, yeah? And driving, you learn the legit way first, you get the license, and then you learn your own shortcuts after, yeah? Same way, fam. Learn the full definition first, yeah? And then after, when it gets to that, when you see it in mark schemes and whatnot, yeah, you'll learn your own definition and your own way of saying it, yeah? Some, yeah, dickheads, they don't tell you, yeah, why it's 1/12 of mean mass of carbon 12 atom, yeah. The reason for that is because the first of all, carbon 12 is bare abundance, yeah, it's bare abundant and it needs to be based on something, yeah. So carbon 12 kind of just makes sense because it's so abundant, yeah. And second of all, yeah, as well, the carbon 12 atom also perfectly, yeah, like perfectly 12 grams of carbon 12 perfectly makes 1 mole. So that's why it has one perfect relative atomic mass unit, the carbon 12 atom, yeah. So that's why it's used and not something else. Isotopes and ions, yeah? Isotopes are atoms of the same element with the same atomic number but different number of neutrons, yeah? Hence a different mass number because mass number is proton plus neutron. So if you've got different neutrons, then it's different mass number, yeah? They have the same chemical properties because they still got the same amount of protons and therefore the same amount of electrons, yeah? So therefore they got the same chemical properties, yeah? But they have different physical properties because something weighs more. If something weighs more, the mass is different, it's going to have a different physical property, yeah? Obviously. Ions are formed when an atom loses or gains electrons, meaning it is no longer neutral but now has an overall charge. So if an atom loses a electron, yeah, or gains an electron, it'll become negatively charged or positively charged, yeah, it'll become an ion, yeah. Time of flight. Time of flight is not hard, yeah, but people bug out over this, yeah. So this measures the time taken for ions to travel a known distance, providing valuable information about their mass to charge ratio. Now listen, if I want to separate something, yeah, let's say they use this for like, for example, uranium, yeah. I got some uranium outside. You go outside, you pick up some uranium, yeah. You got uranium 235 and 238, yeah. 235 is the one that's used for like nuclear shit, yeah. So how am I gonna separate them, yeah, differentiate? What I can do is I can put them in the thermal flat mass spectrometer, yeah. What that means is when I put it inside, the lighter ions they're gonna arrive at the detector before the heavier ions, yeah, or the heavier isotope, yes. Therefore the 235 will reach the detector before the 238. And what that will mean, yeah, is that it then separates the 235 from the 238. Now I've got the 235 that I wanted, and 238 can, you know what I'm saying? It's just on the side. Doesn't matter anymore, yeah? So the sample comes through as a gas, and lighter one will go to detector first, heavier one will take a lot longer, yeah, to reach the detector, yeah? So now the actual steps for this, yeah. First of all, the sample must be vaporized, obviously, yeah. It needs to become a gas so it can flow and move, yeah. Now you got two types of ionization, yeah. Electrospray and electron impact, yeah. Electrospray, the sample is dissolved in a solvent and then injected through a high voltage needle, causing each particle to gain a H plus ion that has been ripped off the solvent. Hence, the sample is now positive. So, the sample is dissolved in a solvent, and then when it's this high voltage needle, yeah, this high voltage, yeah, it rips off a H plus from the solvent, and then it sticks it onto the sample. So now each molecule of the sample, each atom of the sample gained a H plus ion, yeah, each molecule, and hence now it's positive, yeah, so it's positively charged now. Electron impact ionization, yeah, the vaporized sample is bombarded with a stream of electrons from the electron gun, yeah. When an electron collides with a molecule in the vapor, it can knock an electron out of the molecule, resulting in some through sample being positive. Yeah, don't know why I go on there. Yeah. Some molecules can fragment into smaller pieces due to the high energy collisions. Yeah, so electron impact essentially, yeah, you find an electron at an atom, and then what does is that can knock off an electron from the atom. So electrospray becomes positive because you add a H plus ion. Electron impact becomes positive because you're knocking off electrons. Yeah, and again, with electron impact here, because you're knocking off electrons here, the molecule can fragment, it can break here. But that's normally only in like harder questions, yeah. That's not that common for that to come up here, so it's minor. You can neglect that fact, you know what I'm saying? Acceleration, yes, that's the next step. So molecules are then accelerated to have the same kinetic energy. Because all the molecules have the same kinetic energy, the velocity depends on the mass. So deeper, yeah. If this KE, if this has to stay the same, it has to stay constant, yeah. What happens if I increase the M? Well, if I increase M, I want KE to stay the same. I'm gonna have to decrease V because if I didn't decrease V, KE would increase. I'm not allowed to do that. I need to keep KE the same. So therefore, if I increase M, V has to decrease to level that off, if that makes sense, yeah? So therefore, if something's heavier, it has lower velocity, it's slower. Whereas if something's lighter, if M decreases, V has to increase to keep KE constant, yeah? So therefore, lighter molecules are faster. Do you see that, yeah? Now, it's not just enough that they'll reach the detector at different times, yeah? It's also better to have them separated. You see how the NE here is separate to the NE here and the NE here, yeah? That makes more sense. I want to fully separate the ions, yeah? So what I can do, yeah, is the ions enter a region where a magnetic field is applied perpendicular to the direction of motion, yeah? And if you understand from GCSE or even without GCSE, yeah, whenever you put like a magnetic field like that on something that's charged there, it creates a force perpendicular, so it pushes it away. The magnetic field exerts a force on the ions, causing them to deflect. This is called ion drift, yeah? Because they drift away, yeah? Heavier ions deflect less than lighter ions, yeah? And hence the ions are now separated, yeah? Calm. So now, because of this, yeah, the ions will be separated slightly. They'll deflect at different angles, yeah? And they'll also reach the detector at different times, so it's perfect, man, yeah? Detection. The ions hit a negatively charged plate. The ions are positive and they hit a negative plate. Therefore, there's going to be a current, yeah, between the positive and the negative, yeah? And this can be measured on something called an ammeter, yeah? That measures the current in amps, yeah? And the more molecules hitting the plate, yeah, gives a higher abundance, yeah. So the higher the current means the higher more molecules hitting the plate. So if more molecules hit the plate, there's greater current, more amps. If there's more amps, yeah, that means that there's a higher abundance, yeah. And what this is used for is it will show like something like this, yeah. So the 10 will be somewhere at 75%, and the 12 will be somewhere at 25%. These are the abundances, yeah, and this is the relative atomic mass. MZ ratio, it means mass to charge ratio, but essentially it's just a mass because the charge is just plus one. They're all positive one ions, yeah. And what that would be useful is if you remember from GCSE, yeah, for example, argon here, yeah, what you do is you do to find the relative atomic mass here, you do the relative atomic mass of one of the isotopes here times its abundance plus the relative atomic mass of the second one times abundance divided by the total abundance. And then that gives you the relative atomic mass. So that's where they actually get the abundances from. They get it from time of flight mass spectrometry. That's why this is used. Do you see what I'm saying? Because you can compare in any random sample, it will be probability based. You can compare the amps between the 10 and the 12, the boron 10 and boron 12, and you can see that 75% of the amps goes to boron 10, 25% goes to boron 12, and that will allow you to calculate this, the rate of atomic mass here. So that's why this time of flight spectrometry is used here. I know the steps, it's not that hard, yeah? Chlorine spectra. Chlorine is a little bit different. So you need to know about this, yeah? Chlorine can display a characteristic pattern in a 3 to 1 ratio for Cl plus ions. You might be a little bit confused here. All that means here is that chlorine, yeah, like Cl 35 and 37, yeah, they appear in a 3 to 1 ratio. So again, 75%, 25%, yeah. And then a 3 to 6 to 9 ratio for Cl2 because Cl2 you can have different combinations. So you see here you got Cl2, yeah, You got different combinations, yeah? You got 35 for Cl, and you could have 35 for the other Cl. Or you could have 35 for one Cl, and 37 for the other Cl, yeah? Or you can have 37 for one Cl, and 35 for the other Cl. Or you can have 37 for the one Cl, and 37 for the other Cl. So because of these different combinations, yeah, they have different rarities of forming, yeah? And as a result, yeah, you see here, so this is the 1 to 3 rule. Yeah, so you got 35 and 37. 35 is a lot more abundant than 37, yeah? So it will always appear like that. That's a relative abundance. Whereas here, 70, 72, 74, yeah? CO2, CO2, CO2. Again, that's a 3 to 6 to 9 ratio, whatever, yeah? You get that. Calm. Now, the actual subshells, yeah? So they have certain shapes, yeah, that you need to know about, yeah? The S orbital has this circle shape, spherical. P orbital has this infinity sign shape, yeah? D orbital has two infinity signs like that. You just need to know these shapes. It's something very minute, yeah? Just know the shapes and that's basically it'll be pattern. Alright, cool. There's different blocks to the periodic table, yeah? So you got S block here, you got P block here, you got D block here, like DBE or whatever, yeah? F block as well. So SDB, SDP, F, yeah? Remember this, yeah? S, P, D, F, yeah? This will come up. Always just remember SP and then it's easy. The one in the middle is D and then the F one is one on its ones, yeah? So that's very easy to remember, yeah? An S subshell is made up of one S orbital, yeah? A P subshell is made up of three P orbitals, yeah? A D subshell is made up of five D orbitals, and an orbital holds a maximum of two electrons, yeah? Hence, you can see why I go on here, yeah? I told you earlier that S has two electrons. Reason being is because there's only one orbital, and one orbital has two electrons, yeah? P can hold up to six electrons. Why? Because it's got three orbitals, and each orbital has two electrons, so 3 times 2 is 6. A D subshell is made up of 5 orbitals, yeah? Each orbital is 2, so 2 times 5 is 10. Yeah, and F can hold 14, yeah? This is my handwriting allowed, yeah? This is on a whiteboard as well, so it's even worse, yeah? But yeah, is what it is. What this shows here, yeah? You might not understand this now, but I promise in the next few slides you'll understand it, yeah? Is that how you do it is you basically need to fill them up, yeah? So it will go 1s2, that's the first two electrons, yeah? Now I can't do 1s3 because S can only hold up to 2. And then I can't do 1p now because one, the first shell doesn't have any p. So I need to go into 2 and I start from S again. So 1s2, 2s2, 2p6. Now I can't move on to D. I have to go into the third shell, 3s2. And then the third shell there'll be D. Do you see how this works, yeah? The top number is the number of electrons. So 2, 2, 6, 2, 6, yeah? I know this might not make sense now, but I promise in a minute it will, yeah? So electron configuration. Sodium has 11 electrons, yeah? The GCSE electron configuration would be 281, yeah? So you know the first shell has 2, second shell has 8, third shell has 1 electron, yeah? The A level configuration would be 1s2, then 2s2, then 2p6, then 3s1. Now let's break this down, yeah? First shell has 2 electrons here according to GCSE, yeah? The first shell in A level also has 2 electrons, look, 1s2. So there's 2 in the one shell, yeah? Then 8 in the second one. 2s2, 2p6. What's 2 plus 6? 2 plus 6 is 8. So 2s2, 2p6 here has 8 electrons. That's the second shell. The third shell, yeah, 1. 3s1, yeah, so it has 1 electron in the third shell. Easy, man, yeah? So what you do is you fill up like that. 1s2, 2s2, 2p6, 3s1. You see what I'm saying? So you fill it up slowly. So you start with 1, 2. When that's filled up, you move on to the second row, 2s2. Then now that I've used up 4 electrons, yeah, I've got 7 left, so 2p6 and then 3s1. So now do this on your own, yeah. Pause the video, yeah, and do oxygen has 8 electrons, yeah. State the electron configuration for oxygen in this way, yeah. So I'm gonna show you now. Let's break it down, yeah. Oxygen has 8 electrons, right? So let's start. 1s2. 2 electrons have been used. I've now got 6 electrons left, yeah. Calm. Now I can't do 1s3 now. I need to move on to the second shell. So 1s2, 2s2. So now I've used up 4 electrons. I've got 4 left here. 1s2, 2s2, 2p, 4. I don't have to fill the p orbital completely. It can be 2p, 4 here. So this makes sense. 2, 2, 4. That's 8 electrons in total. You see how this works here? I also wrote all the electron configurations, so if you still don't understand what I'm talking about, it might make sense now a little bit, yeah? Hydrogen has 1 electron, so it's just 1s1. Helium has 2, so it's just 1s2. Yeah. Lithium has 1s2, 2s1. Yeah, because I have another electron, I can't write 1s3, so it has to be 2s1. Yeah. Now I have another electron, beryllium, 1s2, 2s2. Now 2p1, yeah, 2p2, 2p3, 2p4, 2p5, 2p6, yeah. Now I can't write 2d, I have to go into the third shell, and again, you always start from S, yeah? Now 3s1, 3s2, yeah? And then you keep going. Do you see that, yeah? When you get to 2p6, yeah? 3s2, yeah? 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, all the way down there, yeah? Now, there's an exception. When you get to the 4s, yeah, is filled before the 3d. That's because it has a lower energy level, yeah? And hence potassium would look like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Yeah? So the 4s1 becomes before the 3d. You don't write 3s2, 3p6, and then 3d1. You write 4s1. That's just how it is. Calcium will now be 4s2. That's just something you need to memorize, yeah? And then after calcium, after the 4s is filled, now you go into D. So then scanadium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So the 4s is filled before the 3d. That's the exception, yeah? Chromium has also there's another exception, yeah. Chromium and copper. This is to do with transition metals. You'll cover it more when you go into transition metals, yeah. But essentially, you just need to memorize it. It's just the way it is. This is rare though for it to come up, yeah. Chromium has an atomic number of 24, and it's expected to end in 3d4, 4s2. However, the real way it is, yeah, is 3d5, 4s1. That's just how it works. So you take one from the 4s and you put it in 3d. This is only for chromium and copper, yeah. So copper will be the same thing. It's expected to end in 3d9, 4s2, but instead you take one from the 4s and you put it in the D. So it becomes 3d10, 4s1, yeah? That's just how it is, in it. There's no way around this, man. You just need to memorize it, yeah? Now, you got noble gas configuration, yeah? So helium has a 1s2 configuration, yeah? That's what helium is, 1s2. Now, neon would be 1s2, 2s2, 2p6. But instead of writing 1s2, 2s2, 2p6, yeah? 1s2 is helium. So I could just write helium, 2s2, 2p6, yeah? Same way, argon would be 1s2, 2s2, 2p6, 3s2, 3p6, but everything before that is just neon, yeah? So I can just say neon, 3s2, 3p6, yeah? You get the idea, and I can keep going down, yeah? Because noble gases have that complete electron configuration, yeah? Because they have a complete outer shell, yeah? And that's why you can do this kind of thing here. You wouldn't be expected to give the answer back like this. This would only appear, I'm just telling you this because sometimes it appears like that, yeah? Normally when it gets given to you like this, yeah, the question wouldn't be about the electron configuration. Normally that's just like a side piece, you know what I'm saying? But yeah, but it's just so you can understand what they're talking about, yeah? Spin. Spin is a quantum mechanical property that describes the angular momentum of an electron along its axis of rotation, yeah? So essentially it's just the way something spins, yeah? It's just the way something rotates, yeah? Around its axis, yeah? So electrons rotate, yeah? So electrons, they rotate around the nucleus, but they also have spin, so they also spin around whilst rotating, yeah? Like the Earth, yeah? The Earth orbits the sun, yeah? But the Earth also spins. Calm. So what you want to do here, yeah, is when you fill in electrons, yeah, you fill them with opposite spin, yeah. So they'll spin in opposite directions, and also, yeah, you fill in them one by one. You don't fill in the same box. So for example, down here on my mouse is, yeah, one. Then down here, I add another electron. It goes in the second box. You don't put it in that first box. It goes second box. Third one, it goes third box. You see. Then you go back round. This jumps from 3 to 6, so this one's a bit of scuffed, yeah, but it should go back round basically. You should have another one here, then another one here, then another one here, yeah. Now there's an exception to this, yeah. When it comes to 3p4, you don't write it like that. You write it as 3p3 4s1, yeah? The reason being is because this creates repulsion. When there's two electrons next to each other, it's a lot of repulsion, and as a result, it has even repulsion when it's in 4s1, yeah? It just levels out. All the spin is in the same direction, and that's just a lot more stable, yeah? It's a lot stable compared to having spin in opposite direction like here. So that's just a small side note. This wouldn't be asked as well, yeah? It's just how it is, yeah? Ionization energy. The minimum energy required to remove 1 mole of electrons from 1 mole of atoms in a gaseous state. Memorize that, yeah? 1 mole of electrons, 1 mole of atoms, yeah? Gaseous state. The equation here says the same thing. Sodium goes into sodium plus E minus, yeah? Again, 1 mole for sodium, 1 mole for sodium plus, yeah? 1 mole for electrons. And they're all gas. Successive ionization energy occurs when further electrons are removed. So when you take up another electron now, so Na plus to Na2 plus, yeah? That's called successive ionization energy, yeah? And this requires more energy because deep it. When I took it out of the neutral compound, the neutral atom, yeah, it's just a neutral atom, it's easy, yeah? I took one out, but now I have to take it out of a positive atom, so it's harder to take an electron out of a positive atom because that positive is going to be bringing the electron in more. because I took an electron out, yeah, there's now more protons than there are electrons, so there's a more force on it. You know what I'm saying? If I got a stone, a rock here, and I got a rope attached to a rock here, and I pull it here, and I'm not that hench here, but I pull it here, and then someone else, I get someone else, he's bare hench here, he's bolo, you know what I'm saying? He pulls it here, it's gonna move even more. Same way, if I have more attractive force, the more protons here, it will bring in the E more. Does that make sense? So yes, that's why if I take one out, it takes even more energy to take another one out, yeah? Calm. A longer period, first ionization energy increases due to decreasing atomic radius, yeah? So you need to understand this. This is a rookie error, yeah? You need to understand this, yeah? When I go across a period, what's changing? The proton number. Proton number is increasing along the period, yeah? Calm. If there's more protons here, there's more positive charge, which means that the electrons will be brought in even more, which means that the atomic radius will decrease because the outer shell is being brought into the center even more. You might be asking though, every time I increase here, the proton number increases, but the electron number also increases, so surely it would balance it. Well, that's wrong. Because proton number and electron number, protons and electrons don't interact on a one-to-one scale. Increasing it by one proton has a bigger effect because that proton affects all the electrons at the same time. It's not a one-to-one ratio kind of thing. Yeah? So that's why if you have more protons along the group here, along the period, it decreases the atomic radius because it brings it in more. There's more greater electrostatic forces here. So hence, if there's greater electrostatic forces and it's held in more, it's going to require more energy to remove an electron. So there's higher first ionization energy here. Down a group. Down a group here, as you know, every time you go down a group here, an electron, there's a new shell. Because of these shells here and the big distance between the shells here, like I mentioned earlier, yes, you're still adding more protons here, but that negates it. It doesn't matter anymore. The loss of attraction between each shell is greater than the gain of attraction between each proton that's added. And hence, the first ionization energy decreases because the atomic radius increases. There's more shells now, yeah? And on top of that, there's shielding, yeah? So the outer electrons are shielded away from the inner force, yeah? Inner positive force, which reduces the effect of the electrostatic forces, yeah? So it's easier to take an electron out from the outside, yeah? If you're going down the group. Now, this is a ionization energy diagram. Yeah, this is easy. You're gonna need to be able to deduce like what type of element this is based on this. Yeah, you might think, oh, that's kind of hard. Yeah, but it's not. It's easy. Every time there's a jump here, deep it. When I go in closer to the nucleus, yeah, it's gonna require more energy to take. Right, so it's gonna be a sudden jump in energy. So in the outer shell, there's just one electron here. I took one electron out. Now there's a big shell to get to the second shell. Big jump to get to the second shell in energy. It increases a lot because now I'm in the second shell. The second shell from the outer shell is closer to the nucleus, yeah? Then I keep taking, and now bang, another big jump here. Now I'm look how close I am. I'm in the first shell. I'm right next to the nucleus here. So it's gonna require a lot of energy to take from here. Now, aluminium is just another like side note you need to know about, yeah. The first ionization of aluminium is lower than expected, yeah. This is due to a single pair of electrons with opposite spin, yeah, and hence the natural repulsion reduces the amount of energy needed to put in to remove the outer electron, yeah. So basically, in aluminium, yeah, one of those boxes, yeah, it has two electrons inside. That two electrons orbiting, yeah, that creates repulsion, and that repulsion, the electrons deeper, the electrons are already trying to escape each other. They're already like repelling each other, so it's going to be easier to take them out. You see what I'm saying? Because they're already repelling each other, so therefore it's easier to take it out, yeah? And that's it, man. That's the end, yeah. Easy, fam. Topic one, yeah. No BS here. Not like this other man on here, yeah. Trying to, you know what I'm saying, yeah? Come on, fam.